So here are some rules for exponents. So kind of the most important rule of them all is the following one. It's that x to the a times x to the b. When you multiply two things together that have the same base, you add the exponents. Wow, I'm writing the wrong thing. You get x to the a plus b. And this is called the additive law of exponents. And it makes sense when we talk about what's going on. If you're multiplying 2 to the third times 2 to the fourth, well, 2 to the third means 2 times 2 times 2. And 2 to the fourth means 2 times 2 times 2 times 2. Well, clearly we're multiplying 7 2's together. So we definitely should write this as 2 to the 7th. So this rule isn't a rule because we're just making up a rule. It's a rule because that's how things have to work. Right? If you multiply 3 2's together and 4 2's together, you're really multiplying 7 2's together. So we add what the exponents are to get the number of 2's that are being multiplied together. So additive law of exponents, kind of a big deal. And then we have some other rules that all kind of actually are results of this first rule. But we're not going to solve as much as first. So if you have two things multiplied together raised to a power, and when I say two things, what I'm really saying is more than one thing. So this rule also applies if you have like x to the a times x to the b times x to the c. You would add all the exponents together. Or this rule is true if you have x times y times z to some power, right? You're going to get, in this case, x to the n times y to the n. And the way I kind of think about it is if you have some product raised to a power, that power distributes to each term in the product. Now, what else do we have? We have x to the a divided by b is equal to, there's a couple ways of expressing this. You can either write it as x to the a inside the bth root, so the bth root of x to the a, or you can actually do the root part first, so the bth root of x to the 8th power, which is actually usually how we're calculating things. And I'll give you an example of that in just a minute, but typically thinking of it this way is usually easier than thinking of it this way when you're actually trying to calculate something. For example, let's just do it now. If I was trying to calculate 8 to the 2/3 power, I could either think of it as the cube root of 8 squared, which I think is easier because the cube root of 8 is 2, right? Because 2 times 2 times 2 is 8. And then 2 squared is 4. Or you can think of it as the cube root of 8 squared. 8 squared is 64. And the cube root of 64, while not impossible, certainly is more challenging, I think, to figure out that the cube root of 64 is 4. Either way you do it, you get the same answer. It's just usually easier to do the root part first and the power part second. We also have that x to the a divided by x to the b is equal to x to the a minus b.
James,
and, sorry, one second.
Oh, sorry. Hi. In the chat, and also I'm seeing it, so it's a little blurry on the right side on the whiteboard.
On this side over here?
Yes.
I wonder what that's about. Let me try a couple things. I was having a blur issue earlier, and the student said it got better, but yeah, I don't know why I'm having problems. Let me see. I try to have my board at an angle to reduce the glare. Let me try moving this side a little bit closer. Does that help at all?
That helps. That's great. Yeah, it's actually clearer. We should keep it like that. Yeah.
Good to know. All right. So this rule here is really just the same as, well, in fact, I'll come back to this in a second. There are two more. We have, when you have a power to a power, so x to the a to the b power, you multiply the powers, you get x to the a times b. An example of this would be like if you had 2 to the third to the fourth power, right? 2 to the third to the fourth means 2 to the third times itself 4 times. So that would be 2 to the third times 2 to the third times 2 to the third times 2 to the third. But that's 2 times 2 times 2. That's 2 times 2 times 2. That's 2 times 2, right? That's 3 twos, 3 twos, 3 twos, 3 twos. That's 12 twos. But that's just what you get when you multiply the powers together and get 2 to the 3 times 4, which is 2 to the 12th. And then the last rule, which I'll write up here. Actually, there's 2 rules I want to say. One of them is not on the list here. That's fine. If you have x to the negative power, to the negative n, it's equal to 1 over x to the n. And similarly, if you have 1 over x to the negative n, it's equal to x to the n. So basically, when you move an expression from the numerator to the denominator, or from the denominator to the numerator, you change the sign of the power. And then the last one I wanted to say was that the nth root of x is the same as x to the 1 over n power. So often, especially when we take calculus next quarter, it's often more useful to write things like this than just to write them like this. So we kind of go back and forth between these very easily. And then the last thing I want to say about this rule right here is that this really is this rule combined with this rule here. So if you write x to the a minus b, that's really the same as x to the a times x to the minus b. But x to the a times x to the minus b is really x to the a times 1 over x to the b, which is just that. So I just want to point out that these kind of all go together. Questions about any of these rules? Okay, a couple more examples. I think it just got darker. Let me do one thing. There, sorry. So, there's a couple more examples I wanted to mention. If I was going to find, say, I'm going to change this example from the one that's in the notes. I want to find negative 27 to the negative 2/3 power. And also we'll do positive 27 in a second. So negative 27 to the negative 2/3 power. So I'm going to think about this in a few ways. First of all, the negative power, I don't like dealing with. So whenever I see a negative power, I'm always going to rewrite that as over the same thing except to the positive power. Like the only thing that's changing about the exponent is that it be from being negative to being positive, but everything else is still the same. And then I'm going to think of this as 1 over, so again, I want to do the root part first and the squaring part after. So I'm going to think of this as the cube root of negative 27 squared. The cube root of negative 27 is negative 3, because negative 3 times negative 3 times negative 3 is negative 27. This is equal to 1 over negative 3 squared. And then that's equal to 1 over positive 9. So negative 27 to the negative 2/3 power is equal to 1/9. Okay. We can do one more. Let's do, I'm throwing in some extras here. Let's do negative 32 to the 3/5 power. And again, I don't know what negative 32 cubed is, right? I don't want to do, I mean, we could try doing it this way as negative 32 cubed and then the 5th root of that. But negative 32 times negative 32 times negative 32 is not easy to calculate. And then the 5th root of that is also not easy to calculate. Instead, I would rather calculate it as the 5th root of negative 32 cubed. Because I know that the fifth root of negative 32 is negative 2. Because negative 2 times negative 2 is 4, times negative 2 is negative 8, times negative 2 is positive 16, times negative 2 is negative 32. So we get negative 2 cubed, and then negative 2 cubed is negative 8. Okay. All right. So those are some of the ways we use rules. We also want to talk about how to simplify radicals. So sometimes, a lot of the time, the things inside a root are not going to be nice, right? Like, sure, the square root of 49 is 7. The cube root of 8 is 2. The fourth root of 81 is 3. But sometimes you're going to be asked to deal with something like the square root of 40. And we know 40 isn't a square number. And we don't want a decimal approximation. What we want to do is simplify this. And when we say simplify this, we mean we want to kind of pull out as much as we can from inside the radical. So I'm seeing this as the square root of 4 times 10. And I know that I can pull out the 4 because the square root of 4 is equal to 2. So I'm trying to kind of factor out the biggest factor that's a square number. If you want, you can take the extra step of writing this as the square root of 4 times the square root of 10. And the square root of 4 is 2. So this simplifies as 2 times the square root of 10, or 2 times radical 10. And that's as simple as it gets. Or we could also look at, say, let's do the cube root of 32. So the fifth root of 32 is just 2, but the third root of 32 we have to simplify. Right? There isn't a nice number that you multiply by itself 3 times and you get 32. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. So this number is somewhere between 3 and 4, but that's kind of all we really know. If I want to simplify this, so the goal is to always kind of factor this in such a way that you have something that's cubic and then the leftovers. You can completely factor it, right? You can write it as 2 times 2 times 2 times 2 times 2. And then I know that I need 3 of the same thing to take the cube root of it. So the cube root of 8 is going to equal 2. I can also break it up, right? I can write this as the cube root of 8 times the cube root of 4. This simplifies, right? Cube root of 8 is 2. This we're stuck with, right? There isn't another cubic factor in there. So that's how this would simplify. And that's generally kind of the idea. So for one more example, let me think here for a second. If I was trying to find or simplify, sure, the cube root of, I'll make something up that's silly, like say 6,000. Here's what I'm seeing. And I just kind of made something up. But I can say that this is equal to the cube root of 10 times 10 times 10 times 6. The cube root of 10 times 10 times 10, since there's 3 of them, the cube root of 10 times 10 times 10 is just 10. This is going to be 10 times the cube root of 6. And 6 doesn't have any factors that 3 of the same number occur. So that's how we simplify radicals when we're trying to pull as much out of the radical as we can. It might not feel like it's really much better, but this is considered simplified compared to that. Now, the reason you might want to do a thing like this is to maybe be able to simplify an expression where you're adding and subtracting things. So for example, again, I know I'm diverging from the notes a little bit just because I know this does come up. If I was trying to add, say, like the, what do I got here? Sure. The square root of, sorry, 1 second. 12 plus the square root of 75. We can't just put those together, right? This is not equal to the square root of 87. It's something that we can simplify though, because 12 is 2 times 2 times 3. And 75 is 3 times 25, which is 3 times 5 times 5. And here, the square root of 2 times 2 is 2. And here, the square root of 5 times 5 is 5. And then I have 2 square roots of 3 plus 5 square roots of 3. And since I have 2 of something plus 5 of the same something, I can add them together. You could either just say it's equal to 7 times the square root of 3, or if you don't like jumping to that conclusion, you could actually factor out a square root of 3 from both of these and say, oh, this is the square root of 3 times 2 plus 5. And then say, oh, that's 7 times the square root of 3. We don't write it like this. We always write the integer part first, so we would write it instead as that. The reason we don't write it like this is because if you write it like this, it can look like the 7 is inside the radical, and that's just not good to make that accidental mistake. Okay, so moving on towards logarithms. The thing you want to keep in mind when you're thinking about logarithms is that they are the opposite, or really the better word is inverse of exponents. So here's kind of the intro. If we have 2 to the x power equal to 8, we know that x is equal to 3. And if we have 2 to the x equal to 16, we know that x is equal to 4. And if we have 2 to the, I skipped one, that's fine. I didn't include the next one. If we have 2 to the x equal to 32, we know that x is equal to 5. And I'm going to leave a space here. We have 2 to the x equal to 64. We end up with x equal to 6. But what if we had 2 to the x equal to 40? Well, we know it's not 5 because 2 to the 5th is 32. We know it's not 6 because 2 to the 6th equals 64. We know it's something between 5 and 6. So x equals some number between 5 and 6. And what logarithms do is they give us a way to express this. So I'll come back to this in just a sec, but let me actually show you how we do this. So the example I typically keep in my head is that there's kind of like 3 different ways I think of this. The first and foremost way is I think about this. 2 to the 3rd is equal to 8. This is equivalent to, that's what this double-sided arrow means. So this and my left right here are the same thing. Log base 2 of 8 is equal to 3. When I read this, here are the words that I actually say. So when I read log base, well, actually I should say, specifically when I read the left-hand side of this equation, when I see the expression log base 2 of 8, the words that I hear in my head are 2 to what power equals 8. That's what I'm asking myself when I say log base 2 of 8. I'm really thinking, oh, 2 raised to what power is equal to 8? And the power is 3. You will also hear people say, and this is true, that logarithms really are exponents. Right? When I'm finding a logarithm of something, I'm finding the exponent. The exponent that if you raise the base to that exponent, you get what's in the argument of the logarithm. So people also write things like, so to get back to the question we were actually looking at for a second, we had written that 2 to the x is equal to 40. Well, this is equivalent to log base 2 of 40 is equal to x. So I don't know exactly what this number is. You could use a calculator to find it, but, or I should say, I don't know what this number is approximately. I do know that x is literally equal to log base 2 of 40. It's a number, it's between 5 and 6. We could find it, if I use a calculator to find it, I would get that it was actually approximately equal to 5.32. I don't need to know that. I don't expect you to tell me that, but I'm just telling you that it is some number between 5 and 6, closer to 5. But this is what we actually care about, that if you're trying to solve an exponential equation like this, where the answer isn't a nice integer number, you're usually going to need a logarithm to express your answer. And then generally, here's what we have. So generally, if we have that b to the x is equal to y, that's equivalent to log, what's the base? What's the base over here? B. So log base b of y has to equal x. I'm always reminding myself that the logarithm is equal to the exponent. So whatever the exponent is over here should be what the logarithm is equal to over here. And that the base is always the same in each problem. And often when I look at something like this, I'm thinking of starting with this, raising it to that, and it's equal to that. So that's often how I'm remembering what's happening with a logarithm. One other thing to remember about this is that whenever you're talking about logarithms or exponentials, the base has to have, there's two requirements for the base. The base has to be greater than 0. If your base is negative, you have problems because negative numbers raised to non-integer powers can be undefined. And we also want the base to be not equal to 1. If your base is 1, you don't actually have an exponential function. A base of 1 means we have 1 to any power is still equal to 1. So a base of 1, you'd actually have a constant function. So our base, and this won't ever be an issue. I'm not going to give you bases that are negative or 1, but just be aware that if you're writing something like this, you should always have a base that's positive and not equal to 1. Okay. A couple other things to be aware of when it comes to logarithms. There are some abbreviations that you should be knowledgeable about. And they are the following. So log base 10 of some number x is abbreviated as log of x. So log base 10 comes up so often that we don't want to write the base 10 every time. So we just decided that we're going to write it as log of x. And we will all agree together that if someone writes this, they mean the base is 10, they just haven't written it. So for example, if I wrote log of 1,000, we would know that I meant log base 10, and that the answer was Well, if we didn't know the answer, here's what we would do. We would say, okay, I'm going to say the answer is x. And then I'm going to rewrite this as an exponential equation. Somebody tell me what's the base that I didn't write here?
10, right?
Exactly. What's the exponent? What's the power? Is it 1,000 or is it x?
It's x.
It is x. And then since I've used up the things, the only thing that's left for it to be equal to is 1,000. And then we can say, oh, I know that 10 raised to the third power is equal to 1,000. So x has to be 3. So log of 1,000 is equal to 3. But yeah, so when someone writes log log, they mean log base 10. They're just not going to write it. Also, the other abbreviation that comes up frequently is that the log, well, in fact, before I say this, I should say, so there's a number. There's lots of numbers, right? There's a specific number. So not pi, but you know that pi is approximately 3.14 something, right? So that's an irrational number. It's pretty cool. There's another pretty important irrational number. And irrational just means, it's got an infinite decimal that's not ever repeating. You can't write it as a fraction. There's another important number, e. And e is approximately 2.7 1828. This is the only number I know like any digits of. So I always feel like I have to show off, right? Like, oh, wow, big deal. He knows 10 digits of a number. But this is the only number I know any of. So I'm like, this is the one thing I know. E is approximately this. But really, all you really need to know about E is that it's approximately 2.7. It's between 2 and 3. It's a little bit closer to 3. And the thing about E is that it is called the natural base. So E is the natural base for reasons that will become more apparent when we take calculus. But there are lots of things very, very nice about base E compared to other bases. So it comes up so often that we don't want to write it every time. So we write log base E of x is abbreviated as the natural log of x. Now you'll hear lots of people say ln of x. It's perfectly fine to say that. I always say natural log of x because I used to actually have an office back when we had offices next to a person whose name was Ellen. And so I would say ln of x, and she would be like, what? Why are you saying my name of x? So I will say natural log. I would encourage you to say natural log. I think it sounds nicer. But if you want to say ln of x or ln of whatever number, that is perfectly fine. I will say natural log. So yeah. So those are two things to be aware of. So if I were, for example, to write natural log of 4, I would mean the log base E of 4. And I couldn't really do much with that. I could use a calculator and get an approximation. The natural log of 4 is approximately 1.38. But I don't really care. I just care that. So what that means is that E to the 1.38 power is approximately 4. Right? Those mean the same thing. But yeah, the decimal approximation is not what's important here. What's important is that when you see natural log of 4, you're like, oh, that just means the log base E of 4. And then I'm thinking E to what power equals 4? And in this particular example, oh, it's approximately 1.38. But really, what we could actually write is that E to the log base e of 4 is equal to 4. Or e to the natural log of 4 is equal to 4. Right? That is actually what's true. Because natural log of 4 is the power you raise e to get 4, e to that power should equal 4. We'll circle back around to this in a minute. But I just wanted to kind of point it out next. It made sense. And then the last thing we want to say, well, no, not the last thing. The next thing we want to say that's always true about logarithms is we can only take the log a logarithm. Doesn't matter what the base is, as long as the base is, positive and not 1. We don't take the logarithm of positive numbers. So why can't we take the log of a negative number? Well, what does that mean? What if I try to take, say, why can't we take, say, log base 2 of negative 8? Good question. Why can't we? Well, again, what does this mean? This means we're trying to find the exponent that's the power of 2, so that 2 to that power equals negative 8. So here's what this says. If we have log base 2 of negative 8 equal to x, what that means is that 2 to the x power equals negative 8. But 2 to any power is going to be positive. It's true. In fact, let me show you real quick. That's not what I wanted to do. Go away. Sorry, 1 second. Let me show you on this graphing calculator. So check this out. If I graph 2 raised to any power, look at that graph. All of the values are positive, right? That graph is always above the x-axis, meaning that no matter what you input for x, whether you input 0 and you get out 1, or if you input, 1 and get out 2, or input 3.3 and get out 10, or something really negative, right? Even really negative numbers still give you positive outputs. So I want to strongly emphasize that 2 to any power is always going to be positive. And that's true for any positive base. If this was a 3 or a 5 or an e or a billion, any positive number to any power is always positive. So this equation, 2 to the x equals negative 8, has no solution. So that means we can't take log base 2 of a negative number or log base any positive number of any negative number. That's why the domain of logarithms has to be non-negative, because this doesn't work for a negative number. It also doesn't work for 0, right? If this was 0 instead, 2 to the x also doesn't equal 0, because 2 to the x is still always positive, which is not 0. So that's why the domains of logarithms actually are what they are. Okay. Let's take a look.
I have a quick question.
Sure.
So like, how you use the example like 10 to the power of x 1,000, and then you had x to the 3. What if the amount on the right hand side like wasn't equal to like anything that's like,
Then,
yeah, like how would we write that?
So then we just leave it as is. So for example, it's a really good question. If we, actually that right there, right? Natural log of 4, we just kind of leave it as a natural log of 4. Or if someone, if we had, for example, say, like log base, 3 of 15, there's nothing to be done. It's just log base 3 of 15, right? Because you're asking the question, 3 to what power equals 15? Well, it's not 2, right? 3 squared equals 9. It's not 3. 3 cubed equals 27. It's somewhere in between 2 and 3. What is it? It's this. It's log base 3 of 15. So that's kind of the weird part about logarithms, is that they often are the answer to a question, but they're not a very nice answer always. So if my question was, like if this was the question, solve this, this is the answer. You can use a calculator to get a decimal approximation, but I'm not going to ask you to do that most of the time. Yeah, so that's kind of the unsatisfying answer, is that logarithms are often the answers, and you don't get much more than that. Most of the questions we look at will have some sort of answer. And I think in the next class, we'll talk more about how, although this is not a nice number, right? This is definitely irrational. There are ways of simplifying this a bit, which we'll talk about in the next class. Well, let's look at some nicer examples, like the following. Like, what if I want to find log base 7 of 49? So be careful. I've definitely seen lots of people say that the answer to this question is 7. We know it's not 7, because we're not saying 7 times 7 equals 49, although we are saying that. But we're asking not what you multiply by, but what power you raise 7 to. So 7 raised to what power equals 49? I want, in 3 seconds, everyone to type their answer in the chat. Well, I'll jump the gun. But yes, you guys are very correct. The answer is, of course, 2. 7 squared is 49. So log base 7 of 49 is 2. They do get more complicated. Like, what about log base 2 of 1 over 64? I know 64 is a power of 2. I think it's 2 to the 6th. But this 1 over thing is tripping me up. So when I get something that's like this one, we could have written, if we wanted to, we could have said this is equal to x, and then rewritten it as 7 to the x equals 49, and solved it and gotten x equal to 2. We didn't need to do that there because it was pretty straightforward. On the other hand, this one, I feel like I do need to do it. So I'm going to rewrite this as, or not rewrite it yet. I'm going to write this as log base 2 of 1 over 64 equals x. And then I'm going to rewrite this. And this is kind of a big deal. We really, really frequently take a logarithmic expression or equation and rewrite it as an exponential equation. The base is 2, the power is x, and it's equal to what's in the logarithm, which is 1 over 64. And then the idea is that we would like to make this side look like something that has the same base as this side. So I would love for the base of this to be 2. So I'm going to make it happen. I'm going to say that 2 to the x equals, well, let's see, 64 is 2 to the 6th power. This is 1 over 2 to the 6th. And then I can rewrite this as 2 to the x equal to 1 over 2 to the 6th is 2 to the negative 6th. And here's something that is true. If you have an equation where the bases are the same, then the exponents will be the same. So you're going to get x equal to negative 6. And yes to the question that was in the chat, the answer will be negative. So if you have an argument here, if the stuff inside the logarithm is less than 1, which 1 over 64 is clearly less than 1, you will end up getting a negative answer. And it's exactly because of this, right? The 1 over 2 to the 6th comes up as 2 to the negative 6. Let's do more. How much time have I got? Oh yeah, I got enough time. What about log base 7 of 1? So here's the nice thing about log of 1. It's always equal to 0. Right. It equals 0 because 7 to the 0th power is equal to 1. And in fact, any positive number to the 0th power is equal to 1. So 5 to the 0 equals 1, 6 to the 0 equals 1, 1,000,000 to the 0 equals 1. And these have to equal 1 because of the additive law of exponents, right? 7 to the 0 is equal to 1 because, well, check this out. What's 7 to the 0 times 7 squared? Well, what do I do with those exponents? I add them. So 7 to the 0 times 7 squared equals 7 to the second power. Oh. Thanks, Maggie. But check it out. Something times 49 equals 49. There's no other choice but for this to be equal to 1. So the whole reason that things raised to the 0th power equal to 1 is because we want the additive law of exponents to actually work correctly. And for this to be true, right, for this to give you this, it has to be true that 7 to the 0th is equal to 1. That's kind of neat. So that means log base b of 1 is always equal to 0 because b to the 0th is equal to 1. So then a couple more. Yeah, we got enough time. The next one is one that often throws people off. I'll remind you, I'm not trying to figure out what you multiply by 8 to get 4. Right? I'm not saying 8 times something equals 4. I'm saying 8 raised to a power equals 4. Just want to tell everybody here, the answer is not equal to 1/2. 8 times 1/2 equals 4, but I want to know 8 to what power equals 4. And again, the tactic we're going to use is to write both sides as powers of the same common base. So we can typically solve questions like this as long as both this thing here and this thing here have a base in common. In this case, the base is 2. 8 is 2 to the third, 4 is 2 squared. So I'm going to write this side as 2 to the third to the x, and this side as 2 squared. And then when I have a power to a power, I multiply the powers. So this is 2 to the 3x equals 2 to the second. And now that the bases are the same, I can say that the exponents are the same. So that 3x has to equal 2, and the x has to equal 2/3. So I can go back and say that log base 8 of 4 is equal to 2/3. Okay, let's go ahead and take a look at the next one. Yeah, we'll get through these.
I have a quick question.
Go ahead.
Can you explain that base thing you just did where you made 3x equals to 2 and they have the same base?
Well, so I didn't make 3x equal to, so from here to here, I said 8 was the same as 2 to the third. I said 4 was the same as 2 squared. And then 2 to the third to the x, I multiplied the powers and got 2 to the 3x. So now here's something that's true. If you have a base to a power equal to a base with a different looking power, it has to be true that the powers are equal. Right? The only way that, right, the right-hand side is 2 squared. The only way the left-hand side is equal to the right-hand side is if this exponent is also 2. Right? The only way 2 to a thing equals 2 to the second is if that thing up there is also the second power. So I'm just saying, oh, this has to be 2. 3x has to equal 2. So the x has to equal 2/3. Because then if I look back here, if x is 2/3, 3 times 2/3 is 2, and then 2 squared equals 2 squared.
And that's only right if they have the same base, right?
Yes.
Okay.
But that's a tactic that we often employ, is that once you can write an equation where both sides are powers of the same base, then it is always correct to say that the powers have to equal each other. Let's look at another example. This one's a little bit more complicated. Log base 16 of the 7th root of 1/32. That looks terrible. So I'm going to rewrite that. Well, I'm going to set it equal to x. And I'm going to say that 16 to the x power equals 1/32. Instead of writing the 7th root, I'm going to say it's 1/32 to the 1/7 power. And again, I'm going to see that both 1/16 or 16 and 32 are both powers of 2. So that Here I can say that 16 is 2 to the 4th. And still we see x. 32 is 2 to the 5th. So this is 1 over 2 to the 5th. To the 1/7. Here I'm going to multiply the powers. I'm going to get 2 to the 4x. Here, before I do anything, I'm going to rewrite 1 over 2 to the 5th as 2 to the negative 5th. To the 1/7. Now I can multiply those powers and say that 2 to the 4x on the left equals 2 to the negative 5 times 1/7 is negative 5/7. And now that the bases are the same, we can say that the exponents have to equal each other. So 4x equals negative 5/7. And then to multiply both sides by 1/4, x equals 1/4 times negative 5/7. So x is negative 5 over 28. So that's what log base 16 of the 7th root of 1 over 32 is negative 5 over 28. Interesting. Okay, I know we only have a minute left, but the last two problems are real quick, so I'm going to throw them in there, even though I know it's a little much, but I should do these because they're really not terrible. Sometimes, although I feel like it's usually kind of silly, sometimes people want you to solve for the base, which I think is weird. But if I did do that, so if I was trying to solve log base x of 100 equals 2, that's going to become, well, if I rewrite this, x squared equals 100. Now, if we solve this, we know that the solutions are x equal to plus or minus the square root of 100. So x is plus or minus 10, right? 10 squared is 100, negative 10, quantity squared is also 100. But we know that x has to be positive. So really our only answer is x equal to positive 10. And I know it's 11:50, but let me throw one more quick one at you. So let's say we have this. Log base x of 27 equals 3/2. And again, we're trying to find the base, which we know has to be positive. So that means I'm going to have x to the 3/2 power equals 27. So how do I solve something like this? Well, what I did here really, without kind of saying it, is I raised both sides to the 1/2 power. X squared to the 1/2 and 100 to the 1/2. And the 1/2 power is the square root. Generally, when you're trying to solve x to a power equal to something, you raise both sides to the reciprocal power. So I'm going to write this as x to the 3/2 to the 2/3 equals 27 to the 2/3. The reason we do this is because when you raise a power to a power, you multiply the powers. So I get x to the 3/2 times 2/3. On the right hand side, I'm going to say I have the cube root of 27 squared. All right, 3/2 times 2/3 is 1. That's why we picked that number. So we get x to the first, which is just x. And then the cube root of 27 is 3. X to the 1 equals 3 squared. So x is 9. There is no plus or minus here we have to deal with. It's just 9. So log base 9 of 27 equals 3/2.